Welcome to the PCI Express Clock Jitter Tool Overview video. In this video, we will cover multiple topics as well as some examples of the PCI Express Clock Jitter Tool. First, we'll discuss what the PCI Express Clock Jitter Tool is. Next, we'll discuss what kinds of data files the tool will accept. For completeness, I'll give a brief overview of the supported PCI Express system architectures. Then I'll give a brief overview of the PCI Express reference clock filters and jitter requirements defined by the specifications included in the tool. We will have a quick look at the reports and what is contained in the report. What is the PCI Express Clock Jitter Tool? The PCI Express Clock Jitter Tool by Silicon Labs is a free tool provided by Silicon Labs that analyzes the reference clock data in various input formats according to the PCI Express base specifications for the reference clock jitter. Since there are multiple generations and multiple filter possibilities, our tool allows you to choose the most appropriate filter for your system. The tool will then perform the analysis and provide a complete, detailed report on the results. The tool configuration can also be saved for future use. The PCI Express specification the tools currently support are the base specification 1.1, the card electromechanical specification 1.1, the base specification 2.1, the base specification 3.1, the card electromechanical specification 3.0, and the preliminary base specification 4.0. At this time, the base specification 4.0 is preliminary in revision 0.7 and is obviously subject to change. We will update the tool as this happens. The general flow for the PCI Express Clock Jitter Tool is pretty simple. Once you start the tool, you will either select a new project or an existing project. This will then take you to the menu to select the type of file, either time domain or phase noise, and also to load the file. After clicking Next, the tool will load the file and do some basic analysis to show the TIE, period jitter, cycle-to-cycle jitter, and relevant AC specifications. If all this looks okay, then you will again click Next and go to the Filter Selection menu where you will choose the appropriate filters that represent your system. You will then click Next one last time to tell the system to do the filter analysis on the ref clock data, which will result in a report being generated. You will have the option at this point to save the report to a PDF and also save the configuration of the tool for future use. The PCI Express Clock Jitter Tool supports both time domain waveforms or interval files from the real-time oscopes and frequency domain data in the form of phase noise from a phase noise analyzer. The waveforms can be differential waveform or two single-ended waveforms. The tool supports multiple time domain data formats that engineers typically encounter when analyzing clock signals. If a waveform file is chosen, you can load in a CSV, a .bin from Keysight or Agilent, a .wfm from Tektronix, and a .trc from LaCroix. The recommended sample rate is at least 20 gigasamples per second. The tool also supports interval files, which is a CSV file that contains the period data from a clock signal. It is currently recommended to have at least 160,000 edges to analyze. The more data you have, the more accurate the results will be. The PCI Express tool supports phase noise data files in a CSV format as well. The CSV must contain two columns, with the first one being frequency offset in Hertz and the second being phase noise in dBc per Hertz. There are three PCI Express system architectures supported by the PCI Express Clock Jitter Tool: common clocked, data clocked, and separate ref clock architecture. Common clocked is where the same 100 MHz reference clock is provided to both the transmitting and receiving devices. Data clocked only has the reference clock provided to the transmitting device, and separate ref clock has separate reference clocks provided independently to the transmitting device and the receiving device. PCI Express specifications include and require multiple filtering operations to be performed on the ref clock data in order to obtain the jitter results at the CDR latch. The reason for this is because some of the jitter will be tracked by the transmit and receive PLLs and some will be removed, so the final result at the CDR latch is the only jitter that will impact the performance of recovering data. In revision 3.1 of the PCI Express base specification, 5 filtering operations are applied to the data: spread spectrum clock separation, a 0.01 to 1.5 MHz step bandpass filter, a 1.5 MHz step high-pass filter, edge filtering, and architecture-specific PLL difference functions. Spread spectrum clocking separation is intended to remove the energy associated with the spread spectrum in the low frequency range from 0.01 to 1.5 MHz in order to define separate low frequency RJ and DJ components. For the 0.01 to 1.5 MHz step bandpass filter, the intent of having a 0.01 MHz step on the low end of this bandpass is to eliminate any 1/f noise in the clock data, since that noise is 100% tracked by the CDR. This band also eliminates the high-frequency jitter components, 1.5 MHz and beyond, that may not be tracked by the CDR. This range is where the low-frequency RJ specification is defined. The 1.5 MHz step high-pass filter completely removes the low-frequency jitter components, taking into account the high-frequency components that may or may not be tracked by the CDR. This jitter will be the dominant jitter seen by the CDR latch, causing system performance degradation. Edge filtering can be done since the data taken for the reference clock jitter measurements is typically done on real-time oscilloscopes that will have noise due to the scope's limitations related to the finite sampling and voltage resolution aperture. A voltage averaging process should be applied at 5 GHz. This can be done most accurately with a Fourier transform filter, but can also be effectively achieved through a voltage averaging process if the FFT method is too computationally intensive. Most oscopes allow you to change the effective bandwidth as well. PLL difference function and max PLL bandwidth function are applied to the reference clock's data, since the intent of the jitter measurements for the PCI Express reference clocks is to determine what the jitter is that is seen by the data latch at the CDR. Clock jitter at this latch will directly impact how much margin the CDR has to the incoming degraded data stream. A typical PCI Express system is the common clock architecture that considers a TX and RX PLL as well as a CDR. All three of these have characteristic transfer functions associated with it that determines how much noise on the clock is either transmitted, tracked, or attenuated. The PCI Express clock jitter limits used in the PCI Express clock jitter tool come from the PCI Express base specification 3.1 and base specification 4.0 Rev 0.7. Each architecture has associated jitter limits in place that are part of the overall transmit and receive jitter budgets. Shown here are the limits for the common clock from PCI Express 1.1, 2.1, 3.1, and 4.0 specifications. This slide, we have the jitter limits for the PCI Express base specification 2.1 and 3.1 data clocked and separate clock architectures. Please also note that the SRNS, which is the separate ref clock with no spread spectrum, does not include a specification at this time. Now let us discuss the final section of this overview, which is the PCI Express clock jitter tool reports. The PCI Express clock jitter tool reports have 6 basic parts. At the top, there's a section that gives the data file and basic information about the waveform in the file. The next section summarizes all the jitter analysis done for each filter. After that, we have the data file TIE, period, and cycle-to-cycle jitter plots if applicable. Following that, the PCI Express clock AC specification and results are provided. These top 4 sections should be the most relevant data needed and will provide pass-fail information regarding each specification. If more detailed information is needed, the next section provides the detailed jitter spectrum plots, jitter results, and filters used to deliver the jitter results for each generation, architecture, and filter selection. The final section in the report contains the filter constants used for all the calculations. Well, that concludes our video of the overview for the PCI Express clock jitter tool by Silicon Labs. I hope you enjoyed it and I hope it's been helpful.